Hello, everybody. Welcome to today's lecture. Today we're going to get started on chapter 4, which is a very short chapter. We're going to finish this within 2 lectures. Probably there's 3 sections total, so I'll probably do 4.1 today, and then about half of 4.2. And then in the next video we'll do the other half of 4.2, and then 4.3. Okay. So this section is called growth. Growth. So it's about how things grow. So what do we mean by that? Well, in the last chapter that we did, chapter 5, which comes after this chapter in the book, it talks about simple interest versus compound interest. So what we saw there was 2 different ways that money can grow. Okay. As it turns out, those are specific examples to 2 different ways that things can grow in general. One is called linear, which is like simple interest, and one is called exponential, which is like compound interest. So we're going to look at those 2 types of growth more generally now. We looked at a specific example in chapter 5, which is money, and now we're going to look at that a little more generally. So there's a lot of things that we can talk about how they grow, right? Like population is a very popular one. How does population grow? And it could be different depending on what species you're talking about, right? Like how does human population grow versus how does animal populations grow versus how do bacteria populations grow, right? There's going to be some different answers there. So in general, there are 3 main types of growth. Okay. There are 3 main types of growth. If we were to represent them on graphs, okay, like this, let me draw 3 graphs here. Then I'll change the color. Okay, if something was growing like this, okay, where it's just a straight line, this is what we call linear growth. Okay, so that means if we plotted its growth on a graph like this and we drew a line, it would look like a straight line. Okay. So what it would look like is we would have maybe, okay, at this time it is we have this much of it, and then at this time we have this much of it, and so this part would be the time, this part would be how much we have. Okay, let me draw some tick marks here maybe. So maybe at time 1 we have 2 of them, at time 2 we have 4 of them, something like that. Okay. And I'll put this into more of a actual context later, like with some real examples. So we'll talk about like what these numbers mean, tick marks. So we haven't really talked about graphs at all in this class. So I'll go over this a little bit too, because that's typically how we represent this kind of thing. So the other type is what we call exponential. And that would look something like this. Okay. So notice how, if we're looking at the rate of how it's growing, at first, it's not growing very quickly, right? The difference between this part right here, this part right here, and this part right here, they're not that far apart vertically, right? But the difference between this part right here and then this part right here, they are very far apart vertically. So this is what we mean when we say something grows exponentially. This is like compound interest, okay? Here, an example of this one, like I said, is simple interest, right? sorry, f equals p times 1 plus rt, right? Where on this axis right here, we have t, and on this axis, we would have f. So at time 1, we have $2. At time 2, we have $4, something like that. Okay. An example of this would be f equals p times 1 plus r over n to the nt. And again, on this axis, we have t. On this axis, we have f. Okay. So as time goes on, f starts growing faster and faster. And the third one we didn't do an example of. This is called logistic growth, which we're not really going to look at too in depth. But the way this would look is actually kind of the opposite of exponential. It starts out getting big really quickly, but then it starts to level off. Okay. If you ever took a college algebra class and you studied inverse functions, you would see the exponential functions and logistic functions are inverses of each other. Okay. So we haven't seen an example of this, but a lot of populations actually are modeled with logistic models. If you think about like human population, for example, humans over the last 100, 200, whatever years, our population has been growing extremely quickly. Okay. But so you can imagine it's kind of looking like this part right here. But you can also imagine eventually it's got to level off, right? There's only so many people that the planet can sustain. It can't sustain that level of growth indefinitely, like in an exponential model. Eventually, there's going to be too many people on the earth, and the population's going to have to start leveling off, maybe even going down. And the logistic model, it doesn't usually go down, it just levels off. But you can imagine eventually it's going to have to go down, right? Whereas something like bacteria can grow exponentially for a long time because they're so tiny that there's nothing really impeding their growth for a long time. Okay. So 4.1 now is about linear growth specifically. So let's start taking a look at that. Okay. So it puts it into the context of money to begin. Okay. It says the first example it uses says starting at the age of 25, imagine you could save $20 per week every week until you retire. And let's just say you're just stuffing the money into your mattress. Okay. How much would you have stuffed under your mattress at the age of 65? And the way we would do this is we'd say, okay, 40 years, 52 weeks in a year. So we would take 40 times 52 times the 20, and then we would just get our answer, right? So with linear models, it's usually something pretty simple like that. There's not a lot to it. I actually remember doing something like this in 5.3 now. Let me think of where that was. Or maybe it was in one of them. We talked about, it was in the savings section. Now I remember. We talked about if we didn't have all of the interest rates and everything, then without interest, this is all we would have to do. We just took the $100 we were saving and multiplied it by 24 months to see how much money we would have. This is something that would be growing linearly. With the interest added in, it was growing exponentially. Okay. So let's look at the definition of what linear growth is now. Okay. So I've just been talking about some examples, but let's actually define the words now. All right, linear growth, we say a quantity grows linearly if it grows by a constant amount for each unit of time. Okay. So it's growing by a constant amount for each unit of time. So that means that between time 1 and time 2, it goes up by however much, say like 5. And then between time 9 and 10, it's also going up by 5. Okay. So it's always going up by the same amount. With simple interest, that's how it was because our interest rate only applied to the principal. So we just took the interest rate times the principal, and that's how much it would go up every year, right? Whereas with compound interest, this wasn't the case. It would go up by different amounts every time because the amount we were applying the interest to was different every time because we were taking into account the previous interest. Yeah. So a good example of this that you would have seen in any kind of college algebra class you took, or any kind of high school algebra class if you've been in high school recently, you would have learned an equation called y equals mx plus b. Okay, we're going to use some different letters here, but I'll just write down this equation y equals mx plus b. So equation you may know. If you don't, it's okay. We'll go over it. But I just want to relate it to something you might already know about. Y equals mx plus b. Okay. So in this case, your x and your y are variables, which are changing all the time. Your m is a fixed number called the slope, and your b is a fixed number called the y-intercept. Okay. Putting this into, a context of how it would actually be used, the y-intercept would more commonly be the starting point. Okay. And the slope would be the growth rate. Okay. You might not realize this, but this is the same form of the simple interest formula. Okay. The simple interest formula, simple interest, F equals P times 1 plus RT. Well, it doesn't look like it's in that form initially, but if we use the distributive property to do P times 1 and P times RT, so we want to multiply P by both things here, we get F is equal to P plus PRT, which maybe we could write it like this instead, so we can see it's in the same form, y equals mx plus b. P, the principal, that's our y-intercept or our starting point, right? Which we know that's what principal means, right? Principal means that that's the amount of money that we started with. And then P times R times T, well, T is the variable here, so that's like our X up here. So that leaves the P times R to be our slope. Okay, the slope, or this is our growth rate, right? The principal times the rate is how much the money is growing by. That's how much it's going up every month, right? So if we had, P was 1,000 and R was 5%, so 0.05, then P times R was 50. Okay. So that's how much the money was going up every month, right? It was going up by 50. So we would have F equals 50 T plus 1,000. And this would be an alternative way to write our equation. And then we would just have to, whatever T was, we would plug that in and it would spit out whatever F is. So if we want to know how much money we had in 10 years, we'd put it in for T there and we would get 1,500. Okay. So we already did a specific example of this, so now we're just doing it more generally. Okay, you can do this with simple interest, but you can actually do it with a lot of things, not just simple interest. Okay. The equation from the book, it's the same equation, it just uses different letters. Okay. So it doesn't use the y equals mx plus b. It uses p of t is equal to p sub 0 plus t times d. Okay. So p of t is using what's called function notation. We have not talked about functions. That's something you would study in college algebra a lot. Essentially, what's in the parentheses here, the t, that's telling you what your variable is. So t is the variable, and then the rest of it should be numbers that you know. Okay, so p sub 0 in this case is the initial population. So we're putting everything in terms of population right now. Okay. I'm trying to talk about it a little more generally, but the book kind of is zooming in and talking about this always in terms of population, but you can really apply it to anything. So this is the initial population, similar to our principal or our B. Okay. It's just written backwards, but same thing. And then the D here, the D is the it's what they call the common difference. So this is it's just another way of saying the growth rate. It's how much are you going up every time. Okay. So how much is it how much is your population growing by every time? And then your T is your time, and your P is your population at whatever time. Okay. So T is your time, and your P of T is your population at time T. Okay. So for example, our population currently is let's just use like here at Simmons as an example. Let's say 200 students. Okay. So our population at Simmons is 200 students. I don't know the exact number. But let's say it's 200 students. Let's say we grow by 20 students every year. How many students will we have in 6 years? Okay. So one point I want to make here is, if the equations have been confusing up to this point, it's okay, because I'm guessing like if you look at this kind of question, maybe it's easier to reason it out, not thinking about the equations. And that's okay. So what you would essentially be doing is going through those equations without actually looking at them. Okay. But yeah, this kind of question is really all the equation is doing. Okay. It's all that it's answering. So we're talking about the equation, but it might seem like kind of an overcomplication. If this kind of problem makes more sense to you, then you're all good. Okay. You're on the right track here. So let's think about this question. We have our population currently is 200 students. So if we relate it to this, that's our P sub 0. Okay. So the 0 here is a subscript. So we would write P sub 0 equals 200. Okay. Um, a letter with a subscript of 0 is commonly used for the starting point. Okay. It's kind of like our population at time 0. Okay. So the 0 itself, though, it doesn't have any numerical meaning. So we're not like adding that 0 or multiplying that 0 on anything. It's just there to name the value. Okay. What's our growth rate? Well, our growth rate is 20 students, which we call D here. Now, the book is shying away from calling it a rate because when we think about the word rate, that's typically a percentage, right? And we're not thinking of that as a percentage anymore. Now we're thinking about it as the actual number it's growing by, which is why they use this different word different. But it's a rate, just not in the percentage sense. Okay, it's talking about the actual number we're growing by, which is why up here it wasn't just R, it was P times R. That's the actual number that our money was going up by. Okay. So if we're just thinking about our equation, P of T is equal to 200 plus 20 times T. Okay. Up here it had T times 20. I'm just reversing them. So we want to know how many students will we have in 6 years. So in other words, what is P of 6? Okay, so this notation is saying what is the population at the time inside the parentheses, which is 6. Okay, so again, we're just using this as notation. The 6 here doesn't have any numerical meaning. It's just telling us to replace the T with 6. So we write it like this. So then we do 20 times 6 is 120. And then 200 plus that 120 gives us 320 students. Okay. So we got 320 students. Okay. So if we were to make a graph out of that, what would that look like? Let me see if I think I can use some shapes here. Yeah. Which will make it look better. Okay. Say we have this. And I'll use some lines here. It's okay, I'll just draw them. Okay. So whenever we're drawing a graph, okay, we have a horizontal axis and a vertical axis. So the horizontal axis represents what we call the independent variable. There's some other names for it depending on the area of math that you're looking at. But like in statistics, it's called the explanatory variable. So this on the horizontal axis, this is the number that we are putting into the equation. So here we were putting T into the equation. Okay, so T is what is changing. It's what we're looking at. So T is the number that we're putting into the equation. So we'd have T here. And the tick marks are just, the values of T. So we'd have time is 1, 2, 3, 4, 5, 6, 7, 8. We only use 6, but we could have all of these. So this is like 1 year, 2 years, 3 years, 4 years. Okay. And then on the y-axis, in college algebra, it'd be called the y-axis, like if you're using y equals mx plus b. On the vertical axis, though, more generally, we have what's called the dependent variable. This is the output of your equation. So the number that you're getting out once you put a number in. So that's going to be your P of T here, which is just we can just write population. Okay, or you can write your P of T. And you can also just write time if you don't want to write T. Doesn't matter. Okay. Oftentimes, the name of the graph will be something like population versus time. Okay. Meaning it's plotting the population as a function of time. Okay, so we're seeing how the population changes as the time changes. um, at the corner here, it's always 0. So time 0. So what is the population at time 0? Well, in our problem, we saw that it was 200, right? We started with 200. So we need to make the tick marks make sense. So just doing 1, 2, 3, 4, 5, etc., that's not going to work because we're going to have to make at least 200 tick marks, really more because this was 320. So let's use a different scale. Let's use like 50, 100, 150, 200, 250, 300, 350, etc. So we're not going to be able to tell exactly where something like 320 is, but we can approximate it pretty well. So at time 0, there are 200 students. So we would put a dot at 200 at time 0. At time 1, well, it's gone up 20 students, so there's 220. So that's going to be somewhere like right here, right? At time 2, it's 240, so that's like right here. Okay. At time 3, it's 260, so that's like right here. And eventually it should look like a straight line. I can't draw it perfectly here, but it should eventually look something like this. Okay. The book will have some better drawings of this. So you can look like at time 6, this is all off scale, so it doesn't look very good. But at time 6, you should have around 320, which according to our scale, it's a little bit off. But don't worry too much about it if your graph's off. You just want it to be close. If you were doing it on a computer, it'll look a little better. Let me show you how it will look on a graphing calculator. Okay, so I went ahead and put it on this online graphing calculator. This is a website called Desmos. It's a great source for graphs. We haven't really talked about it because we haven't really been doing graph. You can see I put our equation over here. You do typically need to use y and x instead of the variables we were using. So I just use y instead of p and x instead of t. But you can see at time 0, the population is 200. And then at time 6, the one that we found, our population is right here, which is about 320. Okay. So this is a better representation of what it would look like. Okay. Now, and then what we would do is we would use this to predict, okay, at time 10, it'll look like this kind of thing. Okay. Now, of course, in practice, something like our school's population doesn't actually grow linearly. It actually kind of is all over the place. Like it, one semester maybe we overall lose like 10 students. The next semester we gain 20. So it's kind of like all over the place. It's not going to look like a straight line like this. So things can also decrease linearly. Okay. So let's think about this example in the book. Example, what is it? 4.1.3. And it talks about a car depreciation. Okay. Say a car depreciates by the same amount each year. Okay. Again, in practice, it probably wouldn't, but it would maybe be close to linearly, so you could use this as an approximation. Okay. So it says Joe purchased a car in 2010 for $16,800. In 2014, it is worth $12,000. Find the linear growth model. Okay. And then predict its price in 2020. Okay. So this is a little bit different because now we're not given the time. Well, we are given the time. Sorry, we're not given the growth rate, or how much it's growing by, or in this case, actually decreasing by. Right. So what do we do here? Well, we know P of t is P sub 0 plus what was it? T times D. Okay. So what do we know so far? Well, we know that in 2010, $16,800. So let's take that as our starting point. Okay. So that means P of 0 is $16,800. And I shouldn't say let's take that as a starting point. It is the starting point, right? Because that's when you bought the car. Okay. So it's not that there's a choice there. That is the starting point. So that means that we know P of t is 16,800 plus t times d. By the way, if you're ever wondering, I put this little like hanging part off the t to distinguish it from a plus sign. So I noticed they look pretty similar there, but that's how I distinguish between them. Okay. In 2014, it's worth $12,000. So after 4 years, it's worth $12,000. So this means that after 4 years, it's worth $12,000. So that means it's $12,000 when t is 4. Okay. So this is what we're working with here. Our P of 4 in this case would be 12,000. Our T is 4. So we're just looking for the D now. So all we have to do is solve for this, and we got to get the D by itself. So we'll do our normal algebra. We'll subtract 16,800 from both sides. Whoops. And over here, we get negative 4,800. Over here, these are 0, and we get 4 times D. And then we just got to get the D by itself, so we divide by 4. And so we get negative 1,200. Okay. So D is negative 1,200. This means that it's going down in price by 1,200 every year. Okay. So our model is P of t equals 16,800. We could say minus 1,200 times t. Okay. So in our final model, t and P of t are our two variables. They're the two things that aren't numbers. 16,800 will always be there, and the negative 1,200 will always be there. Okay. So now we want to predict the price in 2020. Well, it started in 2010, so that's when our time is 10. Okay. So we're going to do P of 10. So we're going to get 16,800 minus 1,200 times 10. Okay. 1,200 times 10 is 12,000. So we're going to get 4,800. Okay. So this is what it would be worth in 2020, $4,800. Okay. Okay. Um, so that's pretty much all there is to linear growth. Okay. Um, I guess I won't get too much into exponential growth today. Let me just, you know, again, the equation for exponential growth is going to look the same as the equation for compound interest, which, if you remember, looks something like this. And there was an later we added on an n, but we can think of something like this. Okay, so I'll just go ahead and we'll put that equation down, and we can look at it a little bit more next time. Okay, the equation. We'll look at the definition and the rest of it next time. And actually, 4.3 is kind of more about exponential growth, so we'll look at both of those together next time. The equation for this one is P of t is equal to P of 0 times 1 plus r to the t. So again, P of t is our population at time t. P of 0 is the initial population. So we're just putting in terms of population this time instead of money. Okay. R is the relative growth rate. Okay, so just how fast the population is growing. Maybe it's going up by 5% every year or something like that. Maybe it's going down by 2% every year. Then in that case, our R would be negative 0.02. We'll look at that more later next time. And then this is time. Okay. So yeah, we'll go more in depth with this next time. So like I said, it'll reflect compound interest. 4.1, the linear growth. This reflects simple interest. Yeah, I don't think I have too much more to say about that. So thank you for watching this today, and we'll really dig into compound interest next time, and we'll do 4.2 and 4.3. So thanks for watching, and I'll see you guys then.